All right, this is an example of solving a system of two first-order linear homogeneous constant coefficient differential equations written in matrix vector form. And we're going to go through the whole example of this one and get the entire general solution. This is going to be the case where we have distinct real eigenvalues for our matrix. So we know that the solution is going to look like an eigenvector times e to an eigenvalue times t. So the solutions will be exponentials. And so we need, of course, the eigenvalues and the eigenvectors. And this is obviously why we practiced doing this recently and why we learned about eigenvalues and eigenvectors. So let's do that. Remember, for eigenvalues, we need to find the determinant of a minus lambda times I, and we need to set that equal to 0. So that here is the determinant of 1 minus lambda, 1 for 1 minus lambda. We want that to be equal to 0. So that is 1 minus lambda squared minus 4 equals 0, which is lambda squared minus 2 lambda plus 1 minus 4, so minus 3 equals 0. And that is lambda minus 3, lambda plus 1 equals 0. And so we have two distinct real eigenvalues, 3 and negative 1. We got to get the eigenvectors for each one. So if we start with lambda equals 3, then to get the eigenvector, we take a minus lambda I. So that's 1 minus 3 is negative 2, and 1 and 4, and 1 minus 3 is negative 2 again, times our v1, v2. Must be equal to 0, 0. This is a system of two equations, two unknowns, and it's a redundant system. We have minus 2v1 plus v2 equals 0, and 4v1 minus 2v2 equals 0. These two equations are the same, so we only have to deal with one of them. So we have 2 times v1 equals v2 from this top equation. We can pick a v1 to be 1, and 2 times that will be v2. So we have an eigenvalue and eigenvector. And the second pair was lambda equals negative 1. If we pick that, I'm going to skip ahead. We get the eigenvector 1 minus 2. So we have both eigenvalues and both eigenvectors. That means we get two solutions, which is what we want for a system of two differential equations. We want two solutions. We have our first solution is 1, 2, e to the 3t. Excuse me. And we have another solution of eigenvector e to the eigenvalue t. Now, to know that we have a general solution, we would need to show that these are linearly independent. And they are. And they always are going to be in this situation where we have distinct real eigenvalues. So we can go ahead and say that the general solution is x of t equals c1 times the eigenvector 1, 2, e to the 3t plus c2 times the eigenvector 1 minus 2 e to the minus t. So there it is. There's our general solution for this system of differential equations.